Right, so we will talk about the introduction to the communication systems. So basically we have generally three different types of communication systems. So first is a wired telephone, or a cellular phone, right? So this is one type of the communication system. Then we can have TV broadcasting, which is only one-way communication. And then third, we have a wireless computer network. So for example, the Wi-Fi and all these different gadgets that are connected to the Wi-Fi, they are part of the wireless network. So the most efficient and effective way to learn about communication system is to study the major functional blocks. So if we know what are the basic building blocks and how does each block work, what is the purpose of each block, then it's easy to understand, the overall working principle. And let's see what are the basic building blocks of a communication system. So first of all, we have an input signal that is generally called an input message. And after that, we have a transducer. So the purpose of the transducer is to bring the message into a more useful form. So for example, this could be a microphone that converts a human voice, which is in the form of a pressure signal, pressure waves. So the microphone converts them into an electrical signal. So this can also be called an input signal, which is now in electrical form. And this goes to the transmitter. So we'll discuss what happens inside transmitters in the coming videos. Then the signal is transmitted. So basically, the transmitter is composed of a modulation part, where the input signal is used to modulate a carrier. That carrier could be it's generally of a high frequency, and after that some property of the carrier is modulated. For example, amplitude, phase, or the frequency, as we have discussed in other videos. We have discussed them separately. Then that modulated signal is transmitted over the channel. The channel could be wireless, it could be a wired channel, a fiber, or anything like that. And then we have what happens at the stage of the channel: distortion and noise is added to the signal that we will discuss in the coming slides. So the signal is then received at the receiver, where the receiver extracts the electrical signal from the carrier or the received modulated signal. And then at the output we have ideally we should have exactly the same signal as we had at the input, but because of distortion and noise, we will not get an exact copy at the output of the input, right? So but it's good enough. Generally there are limits to the noise and distortion, so the signal is good enough generally, and we can extract our voice signal back, our original message signal back, by using an output transducer. So for example, in this case, the output transducer could be a speaker which has an electrical input, and it gives us the sound waves as the output. So now this is the discussion we have mentioned it here as well. So the input could be a voice signal. We have the transducers. Transmitter modifies the baseband to a higher frequency, which is called modulation. Transmitter may have an analog to digital converter as well if it is required, if we want to transmit digital data, right? So in that case, we need to have an A to D converter as well. And so the receiver will have demodulator. It will have a digital to analog converter if we had transmitted a digital message. The channel is generally, as we discussed, it can be a coaxial cable, it can be a fiber, and all these channels are already there. It can be a wireless channel, like we have in the case of mobile phones, and wireless in case of Wi-Fi's. So the receiver then processes the signal. I mean, generally filtering is involved at the receiver to remove out of band noise, and then we get the electrical signal, which is converted back into a message signal through the output transducer. Now, what are the type of impairments that the channel can have? So generally there are three major types. One is attenuation, distortion, and noise. So attenuation, as the name suggests, it's just the reduction in power of the signal when it is transmitted over the channel. So if the length of the channel is large, the reduction in power or the attenuation of the signal would be large. If the length is small, then the attenuation is small. So it's just the simple reduction in power of the channel of the signal. Generally the reason for attenuation is that the signal dissipates some of its power, or it gives some of its power to the components of the channel. So for example, if there are atoms of the channel from which the channel is made up of, it could be, let's say, a wireless link or a fiber link. They start to vibrate they start to vibrate just like with the same frequency, as the signal frequency. So because of that vibration or oscillations, some of the power from the signal is given to the channel. So this is generally the cause of attenuation in most of the channels. Distortion, as the name suggests, it's different than attenuation because we have multiple signals in a channel. So let's say in a wireless link, we know that there are many users, so there are many frequencies that are carrying the information of different users. Now when these frequencies interact with each other, they result in some sort of distortion. So in this attenuation is also called linear distortion, because what happens here is that, as we said, if we transmit a power, a signal having an amplitude of A, we may receive a signal having an amplitude of 0.9 times A, so which is reduced compared to the actual transmitted signal. And similarly, we can have 0.75 times A. So this is simply attenuation, and it's called linear distortion. Now, as I said, we can have other different types of distortions. For example, we transmitted a signal over the channel. At the sender, we have, let's say, this is our signal, right? So from the Fourier transform, we know that every signal is composed of multiple carrier frequencies, multiple sinusoidal waveforms, right? So there can never be a signal that has only one frequency. It will be composed of multiple frequencies, and that is called the bandwidth of the signal. Now, generally, channels are frequency selective, so their response for each frequency is slightly different from the response for one frequency is slightly different from the adjacent one. So if that is the case, when this composite signal is transmitted over the channel, then we have slightly, let's say, this one may be attenuated a bit more compared to this one, or this one may be a bit delayed compared to the adjacent one. And so the signal that we receive, if we combine all these frequencies, so the signal that we receive will be a bit distorted. So remember, this is the signal. It's generally composed of multiple frequencies. From the Fourier transform, we know that. And since it has multiple frequency components, when it is transmitted over the channel, the channel can be frequency selective, meaning that its response to the each frequency would be slightly different, and that's why the overall signal that we receive at the end will be a bit distorted compared to the actual signal, right? So we can say that if the bandwidth of the signal is very large, this distortion, we can expect this distortion to be larger, right? So these type of distortions can be called linear as well. This is also part of linear distortion because it can be corrected by an equalizer. So what is an equalizer? So let's say we, the channel response that we have here, the channel, we can have an equalizer, a device that has an opposite response to the channel, this channel. So for example, if the channel has more attenuation for this frequency, then we can have lesser attenuation for this frequency in the equalizer and higher attenuation for the other frequencies. Or if this signal is delayed more compared to this one, then we can have an equalizer that performs the opposite before the signal is transmitted or even after the signal is transmitted. So this is called post equalization or pre-equalization. Pre and post. Pre is before transmission, post is after transmission. So they can be, linear distortions can be corrected through equalizers. What cannot be corrected through equalizers or which are difficult to correct is nonlinear distortions. Such distortions can also be partly corrected by complementary equalizer at the receiver. It's partly corrected, not completely corrected. So channel distortions, if they are known to us, then we can, pre-compensate them or perform post-compensation. Practical environment. Now we come to the next point, which is the noise. In practical environment, signal can be corrupted as they are transmitted. So what are the sources of these noise or these distortions? So there are generally two sources. One is the external noise, and then the other one is the internal noise. So external noise includes interference from signals transmitted on nearby channels. So although nearby channels have different frequencies, but if they are very close to the actual signal frequency, so they will still have some sort of distortion that would be caused by constructive or destructive interference between the two frequencies. Human-made noise, for example, switches in the electrical equipment that we are using for this purpose, for the communication system. If they are faulty, then we will have some noise there. The ignition system of automobile, they radiate noise they radiate frequencies that are, if they are in the same frequency range as of your signal, then they will result in some sort of noise. Noise from lightning can be, especially in case of if the signal is laser based or an optical carrier is used, then this can cause distortions. We can have microwave ovens, cell phone emissions. If they are in the same frequency band as the signal, then they will cause noise to the signal. So this is an example. We have the transmitted signal, there's channel noise, and then the received signal, as you can see, it's much distorted compared to the transmitted one. Then we have, again, as I said, the internal noise. Internal noise sources can be the thermal motion of charged particles. So we know the conductors are, the charge carriers inside conductors or semiconductor devices are the electrons. So their motion causes friction and heating up. So that sort of that type of noise is called the internal noise. So we can reduce the internal noise, let's say by maintaining a perfect temperature, but they cannot be eliminated, right? So noise is one of the underlying factors that limit the rate of telecommunication, as we'll be discussing in the coming slides. That the one of the major factors which limits the data rate of our channel is the signal to noise ratio. So noise is quite an important factor to be considered for determining the data rates. Then in practical communication systems, channel distorts the signal and noise accumulates along the path, right? So the signal, now the issue is the signal strength decreases while the signal to noise ratio reduces. Now we can say that why not just use an amplifier to increase the signal strength, but the issue is when we amplify a signal that has already been affected by noise, we are also amplifying the noise as well. So that means amplification will not result in an improvement of signal to noise ratio. It will only increase the overall power of the signal, which also has noise in it, right? So then we have analog and digital messages. This is, since it's an introduction, so I would like to introduce all the different concepts here. So analog signal is the type of signal that can take any amplitude, right? So let's say if we have this amplitude, we can have this amplitude. Between any 2 points, an analog signal can take any value, infinite value. So let's say we can have 1.1 as a value, we can have 1.01, 1.001. So that this is what we mean when we say that an analog signal can take on any value. So in other words, infinite number of values between any 2 points. A digital signal, on the other hand, can take up only two values, right? So sorry, a digital signal can take up only a finite number of values, not just two, a finite number of values. Signals that are associated with, let's say, computers are digital because they generally take on two values. It's either positive +5 or -5, depending upon the system that we are using. So a message can be constructed by M symbols, and then in that case it's called an M array message. So the number of levels that a signal has, that can be called M symbols, and accordingly the message is called M array message. Now this slide explains the difference between all the different type of signals. So in this case, this part A is the figure A is an analog signal, and it's continuous time. It's analog because it can take up any value along the y-axis. It's continuous CT because it can, the time can have any value along the along the x-axis, horizontal axis. In figure B, we have a digital signal because it is taking only two specific values, but on the time axis it's continuous, so it can take on any value on the time axis. So it's called a digital continuous time signal. In this case, the signal along the y-axis can take any value, so it's called analog signal. But on the x-axis, we can see it can only take discrete values of time, so that's why it's called an analog discrete time signal. And finally, we have a digital discrete time signal, where we can see the signal is taking only two values along the y-axis, so it's digital, and along the x-axis it can also take some discrete values, so that's why it's called discrete time. So the analog or digital is determined by the y-axis, and discrete or continuous is determined by the x-axis. So what is the significance of analog and digital signals? Digital communication is generally more rigid because it has only a set number of values. Let's say in the binary case, it can have plus A/2 amplitude and minus A/2 amplitude. So where one of the amplitude represents ones in the data and the other amplitude represents zeros in the data. So the receiver now only needs to detect what is the amplitude, if it's positive or negative, and it will know that the transmitter transmitted a 1 or a 0. So this is a figure which explains this process. So we have a signal that has a value of positive as A/2. So let's say this represents a 1 in the data, and it has a value of minus A/2. So let's say this is representing a 0 in the data, and this is how this could be 1, 1, 0, 0, and 0, right? So now if this signal is transmitted over the channel, we will see it is distorted without noise because there are other sources of distortions as well. Then the received signal has noise in it, so this will be further distorted. But at the receiver, we only need to detect if it's a positive amplitude or a negative amplitude, and based on that we can still extract the same information, that if it's a binary 1 or a 0. and so we can determine what the transmitter has transmitted. If you want to further retransmit this signal, that is called a regenerated signal. So we can again give it, reshape the signal back to its original form and then retransmit it to further longer distance. So that process is called a repeater, where we are transmitting the signal again, and this requires a regenerator, and this is generally used to increase the length of the system, and this results in improvement in signal to noise ratio, because once we have got our signal back like this, so the signal to noise ratio will be improved. If you are only performing amplification, this will not improve the signal to noise ratio. It will only amplify both the signal and noise. So now, how do we perform? What is the relation between, how do we move from analog to a digital signal? So that is done through an analog to digital converter, which is generally called A to D conversion. We will be discussing this later as well. The first step in A to D conversion is to sample the signal, right? And then we give each sample a number, right? So now this is done in two steps, right? First is the continuous time signal is sampled into discrete time signals, and then we have a sampling theorem which states what should be the sampling rate, how many samples per second we need to get the signal back from its sample, to reconstruct the signal. So from Nyquist criteria, we know that it should be at least 2b, 2 times the maximum frequency in the signal. So if the maximum frequency in our analog signal is B, the number of samples, minimum number of samples should be 2B. They can be larger than 2B, right? So then the second step is to quantize this signal. The samples are quantized. So this figure shows the process. So you can see on this axis we have the samples, right? Each sample has a different value depending upon the signal. The analog signal in this case is a sinusoidal signal, and this is the range of values that we can give, we can assign to each level. So this is, for example, assigned this value, this sample is assigned this value, and so these are numbers on the y-axis. They are they are plotted between minus MP and MP. The number of intervals L is specified. It's different for it depends upon the type of communication system we have. So once we have the numbers here, we convert them into binary numbers, and then we transmit them over the channel. So as I said, the number of levels depends upon the type of system we have. We can have, these numbers should be raised to the power of 2 to the power n. Generally they are, in fact almost always they are to the power n. Commercially, the number of levels used is 128 or 256. So remember, the larger the number of levels we have, the better the signal reconstruction is even better if we have a large number of levels here, because the difference between even the small differences between the samples can then be correctly transmitted towards the receiver. Now we finally discuss what are the advantages and the disadvantages of this communication system. So one thing is the implement is generally, because it's very, we have 8 converters very common, so they are very expensive. Is excellent because just need to detect in a digital signal, we need to detect 2 binary levels. We can perform error correction as well by using some sort of coding, and then we can encrypt the data as well. So instead of transmitting the actual data streams, we can add some encrypted extra bits to the signal just to make it more secure. The disadvantages are we need to have synchronization at the between the transmitter and receiver. And obviously the bandwidth requirement is high because the number of bits transmitted per second is high.